class. Today we're going to be looking at section 2.8 from our AP Stats course. This is kind of just a continuation, what we saw in 2.7, which is linear regression. We're just going to talk about a few things here. I'm going to kind of jump around a little bit, and anything I don't cover in this video, make sure you get from our calendar and the filled in notes note file there. So the first one we want to talk about is the danger of extrapolation. So it is inappropriate to make a prediction for y values of x values outside of the given range of data. So when what that means is if I'm given a range of data, so I'm given a bunch of data and I'm doing a linear regression, I run my regression in my calculator, I find the line of best fit, I can use that regression line to make predictions for what the y value might be for x values that weren't necessarily in my data. The problem is that line really only applies to our data from the minimum to the maximum x value that we were given. So anything before that or after that, we can't assume that the line would continue in the same way. So that's what we call the danger of extrapolation, is don't make any predictions for data values or for x values that are outside of your data range. Specifically, and well, not specifically, that's kind of overall, but also when the x value is time, it's really important. Extrapolation becomes an attempt to peer into the future or into the past, which is definitely something we want to avoid. All right, I'm going to skip down to talking about outliers, leverage, and influential points. So a lot of these are really similar. They're kind of all in the same category, but they have different, slight differences between them, and it can be a little tricky to keep them separate. So hopefully these examples will help you. So an outlier is a data point whose y value does not follow the general trend of the data. So, so anything that's out of the general line of your data that's like really far off, you can consider that an outlier. They often have large residuals, or they might be high leverage points which don't have high residuals. So we'll talk about that also. A data point whose residual is large always deserves special attention. So we always want to definitely look at points that have large residuals and figure out what's happening there. If the point has an x value far from the mean of the x values, so if we think about all of our data is like in a group like this, the mean of the x, so roughly the middle of our x values, if I have a point that's really far away from that mean of the x values, the point is said to have leverage. And now I wrote high leverage here. I'm going to put high in parentheses. It has leverage, just basic definition of leverage, if the point has an x value far from the mean, but it really only has high leverage if it also changes the slope of the line. So I'll show you an example, but pretty much if the point is far from the mean of x, it means it's going to be kind of on the ends of your data. And if it's not in line with the rest of our data, then it's going to kind of twist that regression line toward it and away from where it should be. That's what we call that high leverage point. A point with high leverage has a potential to change the regression line, but it doesn't always. So, and now again, a point with leverage might not change the regression line. A point with high leverage usually does. If omitting the point from the analysis gives a really different model, specifically the slope, then the point is said to be an influential point. And since influential points pull the line close to them, they often have small residuals. So don't just look at the residuals to see if something's out of place. Definitely want to look at your graph. You'll see influential points more easily in your scatter plots of the original data or by calculating your regression model with and without those points. So let's look at this next piece here. And this will kind of hopefully visualize this for you and make a little bit more sense. So we're going to go through each one of these three problems and decide if that point is high leverage, has a large residual, and or is influential. So if we look at this data, this point for number one that the arrow is pointing to, it's not really far away from the mean of x. Like if I think about the mean of x being somewhere close to the middle, it's not really far away from that. So it's not going to be a point with any leverage or high leverage. Now, because it doesn't really have that leverage and it's not towards the end of our data, it's not really going to be twisting our line. It's kind of like, imagine like a seesaw, I guess. If you sit on the ends of your teeter-totter or seesaw, it's going to move that seesaw, towards, you're going to influence that seesaw. But if you like sit towards the middle, it doesn't really move as much. And that's kind of what's happening here. If that point is sitting towards the middle, it's not really going to move your line very much. So it's not going to be an influential point either, which means our line of best fit is going to pretty much follow those other points. And then this would have a really high residual. The residual is the difference between the y value of that point and the predicted y value on our line. All right, so then this next problem, problem 2, if you think about the mean of x is probably like somewhere over here, then that point is really far from the mean of x. So yes, it's going to have a high leverage or leverage point. But if we draw our residual line, it's kind of in line with the rest of it. It's not really far off from where that line would have predicted that it is, which means it's not really going to have a large residual, and it's not really going to be influential. It's not going to be changing that line much because it kind of lines up anyways. Now, this example 3 is definitely kind of hits all of our points here. So if our mean of x is somewhere in the middle of this cluster here, and my line should look something like this, unfortunately, that point being far away from the from the mean of x's, so it's kind of on the edge of our seesaw, and it's not in line with our data, it's going to take this line that should have been like this, and it's going to twist it towards that point and end up something like this. Now, because it's doing that and it's so far away from our points, we probably are still going to see a fairly large residual here when you have, and it is an influential point because it is changing that slope of the line. It's sitting on the outsides of our seesaw and not in line with our data. And sometimes when that happens, it pulls the line so close to it, it doesn't really have a large residual, but I think this one will because the other points were so drastically in the other direction. So hopefully that helps you kind of get the feel of what these outliers are categorized as, if they're leverage points, high leverage, they have large residuals, influential points, that sort of thing. All right, and then let's see what else we're going to go to. I think, you know what, we'll do one more piece. So on the 4th page of our notes, we're going to talk about interpreting slope. So, so slope, just like any other linear equation, slope is going to be the number that's connected to your x variable. In this example, we have the number of calories in breakfast cereals related to their sugar content. So sugar content is going to be our explanatory x variable. The number of calories is going to be our y, our response variable. But we need to be careful when we interpret the slope, and this can be a little tricky. Interpreting the slope, we can't imply causation. We've talked about this before. Correlation does not imply causation. So in our wording, we have to be really specific to make sure that we're not saying that this change will cause this change to happen. So an example of an incorrect interpretation, it would be something like adding. Now remember, slope is like 2.50 over 1. So it's a change in y over the change in x. So it would be saying, so like this is y over x. Remember, slope is rise over run. So it'd be saying something like adding 1 gram of sugar, which is our x, is expected to increase calories, which is our y, in breakfast cereals by 2.50 calories. Now, this is a bad and incorrect interpretation of slope because it's literally linking the two as if it will cause the other to happen. Adding 1 gram of sugar will increase your breakfast cereal by 2.5 calories. That's saying that this is going to cause this to happen. This is not good. No causation is allowed to be implied. So what we can do instead, so here's a correct interpretation, would say something like this: on average. And that's a pretty important piece to have. A slope is an average rate of change. So on average, cereals having 1 more gram of sugar tend to have about 2.5 more calories. Now, I'm not saying why. I'm just saying that this tends to show this. It could be for some other reason, but I'm not implying causation. And I have a lot of what I like to call wiggle words in AP stats. On average is important. It's an average rate of change. But the whole tend to have and about this much, those are my wiggle words, and they just kind of keep me safe. So I'm not being so black and white, and I'm definitely not implying that one causes the other. And then that's going to be it for our lessons today.